Hey, recording. Um, this is Understanding Bitcoin Source. And, oh, I have to switch the mouse. There it is. And today I wanted to do it on peer messaging. We'll see how this goes. Um, why isn't the slide changing? There it is. So, I was going to say, first, there was one. One Bitcoin node is the first one that's spun up. And the value in Bitcoin is having a peer-to-peer network, right? Having everyone connected. So, in here, this is kind of cropped on the Twitch stream. Oh, and I can move it through here. Cool. Let me fix the dimensions of the screen a little bit so you can see the whole thing. All right, I think Roz was saying I was going to drop the Twitch link for this. I thought I was going to say I was going to put it for CPR in the chat. I was like, CPR advertising wouldn't be that great over here with the viewership. How is this looking? All right, let me actually go refresh.
Let me see it on my phone.
Yeah, it is. Okay, first there was one. Let's just see if I move this up, is it out of frame? I think it's good, right?
Oh, on Discord?
Oh, on Twitch. Oh yeah, the link I think is on Discord. All right, so I think it's okay. So my dramatic, first there was one Bitcoin node. And then after there was one, there was two. So this presentation is the story of how that one node turned into two, and then how that one turned into a relay network of 10,000 from the network of two. As best as I can explain it and as coherent. So what does peer messaging define? What is peer messaging? Abstractly, I like to say it's the language of Bitcoin nodes. It's how nodes... it's sorry, I got the notification too. I felt it vibrate. But yeah, abstractly, peer messaging is the language of Bitcoin nodes, and it's how nodes talk to each other. I say that peer messaging is the underbelly of Bitcoin's censorship resistance. The peer-to-peer protocol is how most transactions get relayed between nodes, and it is vital to the Bitcoin network. That's why I thought it was so important to at least touch upon. And in realer terms, the format of messages nodes use to request and share data is what peer messaging defines, as well as the management of connections to peers. Since not all peers are friendly peers, some are a little malicious, or just have ill-configured settings. But with all the different computers and all the different node versions, it could be a pretty daunting task to think of how they can all coordinate to relay transactions across their networks. And I had this GIF that took me like 10 minutes to add. It's only the only one in in this. So I wanted to go step by step. Before looking at the code, I just wanted to go over high level functionality of Bitcoin in terms of peer connections. There are screenshots of code in this presentation, but it's not super focused on it. So it all starts with start. See, I have this little code snippet, and in Bitcoin, you could actually see this start method in it. And it initializes everything that Bitcoin needs. It has the I2P connection support, which is privacy network. It's kind of like Tor. And relevant to what we're doing, it has this line, or these lines that pertain to DNS seeds. When you first spin up a Bitcoin node, who is it going to talk to? Who do you know with the Bitcoin node no one typically, if you're just getting into it, you're like, let me download the software. But you need to get the information from somewhere, right? And that information is actually hard coded in Bitcoin. So, in a way, you could say people who are using Bitcoin Core are, centralized in the fact that they all start off with the same people giving them information about which nodes to pull information from. And we have the names and the URLs of these DNS seeds in this next slide. So yeah, this is where all Bitcoin nodes pull from. It's various respected developers in the Bitcoin community. Like Peter Woolley, he's a guy who was working at Google doing a lot of cool cryptography stuff. I was checking the messages, but I think you would tell me if someone said they couldn't get in or something. Right? But yeah, Peter Woolley, very important guy in Bitcoin. So is Matt Corallo, Luke Dash Jr., who just released his Oceans pool. Christian Decker, I work with him on Greenlight. Jonas, Peter, Strors, Stefan, and Jason. I don't know these two names, but everyone else is like I have heard of before. They're big Bitcoin developers. So everyone, when they start up their node, they are seeded by these people on who to connect to in Bitcoin. It doesn't mean that you're limited to these people. You could, if you have a friend and they have a Bitcoin node running, you could ask to get information straight from them. There are these things called like RPC calls you can make on your Bitcoin node. So you can make a command that says, hey, I just want to connect to Mars's node. And I just want the information from him. I don't want to be seeded by these people because I don't know these people. But we do trust them. There's an implicit trust in these developers. And most people don't really stray from the defaults too much. But yeah, announcing ourselves. One of the first things that Bitcoin nodes do when they get up and running is they announce themselves with a version. So this is a method called initialize node. And you get your node ID. You don't really have to worry about this too much. The important part is this, really, push node version. And push node version essentially will push the version of your node to your peer. Yeah, that's the only way I say it. And it does that if this is like, this exclamation mark is not. So if the peer is not like an inbound connection, then you want to like give them a little handshake by saying, here's my version, right? And the message semantics. So talking about message formatting, these in the code, message are kind of namespaced with this net message type, and here it usually has the message type, and we can look through all the different message types in the code after the overview. And there's a kind of semantic to how messages are formed. So when you look at the code, these message types, if they start with a verb and then have like some piece of data after, or a word for data like transaction or block, these messages are typically requesting an action to be performed by a receiving node. Yeah, so like I'll be like get block, and then I'll send that to you, and then you service me with data of like the blocks that I'm asking for. Data, it's like if I just say block, then it means I'm just giving you data. So it's either I'm like demanding something from you or I'm giving you something. Sequence diagram. When nodes start up, I mentioned this version. So yeah, something will send a version message to another node, and the node will send a version message back whilst doing some other, verification. Yeah. And then it'll send a verification acknowledgement, and when node 1 receives that, it'll send headers, and then node 1 will eventually give a version acknowledgement, and then node 2 will give the send headers as well. Yeah, the var-ack is version acknowledgements. And the execution path is, again, starting from the start that we had. There's this thread message handler that it goes into. And this thread message handler is like a coordinator who like kicks off a whole bunch of different jobs that it wants the Bitcoin program to do. or when it says, hey, I want this one job to be processing messages, and I want another job to be sending messages to people for me.
Mm-hmm.
So in process message, we process requests from our peers. We service existing requests before trying to process new ones. So we're not overrun with data. And then the real logic is in this process message, which we'll look at. And in send messages, we try to send headers to our peers saying, hey, like, this is where we are on the blockchain. Let me know where you are. That's kind of what we're saying. We also send these things called like inv messages, which is short for inventory messages, to pairs of blocks and transactions we have. So inventory is, I don't really send you all the data. I just say, hey, this is a hash, and this is corresponding to a transaction. Or this is a hash, and this is corresponding to a block. So an inventory is a basket full of these different types of messages with just a hash and a type.
You can pull from
Right, yeah. So
anything in that batch.
Right, exactly. So I give them all to you, and then you have to look at the hashes, and if you're missing one of them, then you come back to me and say, get transaction, and then I'll be like, all right, here's the transaction you want. So yeah, we request data we know the peer has that we don't, with these inventories. That's how we're able to sync up with each other.
Right.
So what happens when a peer lies to us? They have different ways for managing malicious peers like this. Maybe punish node for block, and maybe discourage and disconnect. Also something called consider eviction, which we'll look at. And I think this is the last of the slides. Huh? How often? That's up to each of these individual nodes. You'd have to query each of the nodes to ask how often they disconnect. But that's all the slides, so I'm just going to go back through them and actually try and identify pieces of the code which these belong to. So this cconman start, so it's just like connection manager, that's what this stands for. So not just like, conman. Yeah. But it's a good way to remember it. Conman start. I'll make this a little bit bigger. I think that's okay. Yeah, again, everything starts here. And there's a lot of code here. So I didn't want to go through every line. It's kind of confusing. So I was just going to pick out relevant lines, that I care about. This is one of the lines that we looked at. And this like DNS part. Mm-hmm. In start, you have this thread DNS address seed. And this is where we actually pull from these places. And I think somewhere down here, we should, is it not? Somewhere. Oh yeah, these are all comments. Yeah, we could read through these comments.
Oh, they're just comments that are in there.
Yeah, these aren't my comments either. These are the comments, that other people have written. It's just part of Bitcoin Core's source code. So we have intention that's put into the code. So goal, only create DNS seed if address need is acute. If we have a reasonable number of peers and Adderman, which stands for address manager, spend some time trying them first. This improves user privacy by creating fewer identifying DNS requests, reduces trust by giving seeds less influence on the network topology, and reduces traffic to the seeds. So it's basically saying if you have any other addresses to use, let's try and use them. Don't always try and query all these DNS seeds. When querying DNS seeds, query a few at once. This ensures that we don't give DNS seeds the ability to eclipse nodes that query them. Yep. Hey, Prav, I saw a message. Oh no, he's not here. He's here. Yeah. If we continue having problems, eventually query all the DNS seeds, and if that fails, also try the fixed seeds. So, just talking more about these seeds, you have a lot of this code dealing with the address manager and all these different seeds. So here's where you can actually find the seeds. This is a for loop. So this is going to go for every seed in our list of seeds. And our list of seeds can be found here. At the top, we have this variable. It's of type, it's a vector of strings. And we get it by looking at these m params. These m params should be it's something called chain params, and everyone can configure their own chain params. But there are some default chain params that we could find. You kind of it's not a nice, smooth, coherent scroll sometimes through the code. You have to like look for the things you want. So I know I'm trying to find the seeds, so I'll put v seeds, maybe not equal. And here we see the chain params. So these are the default configuration for your Bitcoin node. It's these things called like chain params, and these DNS seeds are just like another one of these chain parameters that you could add. Well, v seeds specifically is part of this chain parameters, but there's a whole bunch of other things that is set. So the Genesis block, this part in this chain parameters, if you were to change this, you would no longer be on Bitcoin anymore. You'd be on something else. So create Genesis block very much needs to stay the same. Hash of the Genesis block needs to stay the same to connect to the correct Bitcoin network. But all these parameterize an individual's Bitcoin node.
So when you're connecting your node, you have to make sure that all those are correct.
Right, exactly. From wherever you downloaded it from. If you got it from GitHub, most likely it's going to be trusted, good source. But if you want to verify things yourself, if you for whatever reason got a different implementation of Bitcoin, you could check these hashes against whatever the new implementation that you're using has. If it's like BTCD or Bitcore's JavaScript node. But yeah, so these hashes are necessary. You cannot change these, and if you do, you're not on Bitcoin.
Yeah.
On the other hand, if you wanted to fork Bitcoin, it'd be a very
you might just turn that into a
yeah.
yeah.
Yeah. Yeah, I think that'd be pretty cool. I'd get it. Or along the arms, the hash. Yeah, we can go back. So I just wanted to show the DNS seeds for a little bit. We can go back through the code. So yeah, this is how Bitcoin manages these DNS seeds. It goes through every seed. Seeds right now equals 0. If it is, then these are the amount of seeds that you want to create at one time. It is 3 at a time. And I could see this just by kind of hovering over it. It's like defined in a different file, net.cpp, but it is helpful to have this information. Did I just lose where I was? No, right here. So yeah, basically it's saying if we're not getting seeded right now, we're gonna add seeds right now 3 to the ones that we want to pull information. If address manager size is greater than 0, then we will wait a couple seconds before querying the DNS seeds, and we define this time up here, which is not super relevant. And then while the to-wait count is above 0, let's see here, interrupt sleep, this is not too important. This part is kind of important. So we'll go through every node in M nodes, and if one of the nodes that we have stored somewhere is successfully connected, and it's a full outbound connection, we mark it as a relevant node. So, and again, all this only happens if our address manager. Yeah, it's like kind of hard to manage what I want to talk about, and like what I shouldn't talk about. The code is kind of complex, and it's like a lot of it.
Yeah, that's great. I love looking at it.
Yeah, it's like interesting. I also have the first iteration of Bitcoin stored on my computer, and I use that for reference. And it's a lot simpler than this, and that's why I kind of like looking at it more. So maybe I'll switch to that version because again, this covers a lot of different edge cases, and that's why the code is so long. But the original version of Bitcoin is very simple. It gets straight to the point. You can understand things a lot easier. See here, you have like these interrupts. Loading address from DNS. Well, nothing's weird about this one. Proxies, but there's a lot of a lot of cruff. So actually, let me try and get an older version of Bitcoin here so that we could use that as a reference as well. And I thought I had it up here somewhere. One moment. Oh, actually, is it here? Yeah. So I have this thing called Bitcoin Archive, where I went through the first version of Bitcoin and I tried to comment every single line of the code. and I try to differentiate my comments with Satoshi's by putting Satoshi start and Satoshi end, which I sometimes get lazy with, and put SN sometimes instead of Satoshi end and S start. But yeah, I was looking at the process messages here, and this is a lot simpler. So I was talking about the version command is one of the first things that is given to another node. And here you could easily see how we process version commands. So
Just version.
yeah, it's just version. Just has the whole word version here. But yeah, if the string command was version, then what we do at this point is we'd if the node's version isn't equal to 0. This is the first version. So yeah, if the version that we got from another node wasn't equal to 0, we'd say we cannot process this message essentially. Because it's someone else who's doing something with Bitcoin that Satoshi wasn't. We declare this thing called end time. We declare an address. vReceive populates each one with a version message. Okay, if the version is 0, return false. I had a lot of questions when I was looking at it. P from end version. Yeah, let me take a quick look.
So that return false isn't active? Is that asking if they should do it?
Well, this was the first iteration of it. Yeah. So maybe it was the first version was 1, because over here he just checks if it's not equal to 0 and he returns false.
Gotcha.
But then here he returns 0. That's why I think I put the question mark. But
oh, so you put the question mark.
I put these question marks. Yeah. Right, and these comments were a while ago. These are 2 years ago. But yeah, here is I was saying that you could read, I guess, the end version from this vReceive. This vReceive is a stream of data that you're getting from a different node. And what was P from initialized to here? Sorry, I'm going to take a quick... So process messages exist in the new Bitcoin, and it exists in the old Bitcoin, and I like when there's consistency between V1 and the other versions. We used to do these things like these forever loops. And he used to just, keep looping through these process messages. He had some pretty nice logs that you could look at. In the vReceive header, let's see. vReceive size. Yeah, let's just look all the way past here. All right, let's look further into version because, maybe the initial version wasn't 0. Maybe it was 1. And over here, maybe because it wasn't initialized, we said return false. Yeah, that's just me guessing. All right, we set version. We can actually see what he set the version to. Oh my goodness, is it nuts? So search path not found. Oh, I know why. Oh boy. Great. I moved this folder, so I think it's complaining about that. 1 second. Oh. Intermission. I messed something up. I just need to fix it real quick. Oh, there it is. That's what I want. And then here, the desktop. 1 moment. Just fixing something. There it is. Oh yeah. Yeah, I like the aesthetic of it. All right, back to Bitcoin Archive. I think it should work now. Yeah, there it is. Okay, end version was actually 1, it seems like. Yeah, I'm trying to look at the first version that was set in Bitcoin. I'm thinking it was V1, just because I see a 1 here. But I see a lot of end versions equal 0. And again, his code isn't the easiest to understand sometimes. But here, let me go back to the messages. Let's try not to get too far away from that. version. Okay, anyway, we set the version. Okay, 101. That is not what I was expecting. So yeah, this version 101. For whatever reason, that's how it was. Don't mind this other name. He's someone who copied the code. Yeah, there's someone who copied the original code and forked it in his own code base, and I took it from his code base instead of the main one. If we send, if we receive, yeah, whether p from is a client depends on if services. So yeah, this is just handling of the version. Again, a lot of cruft for the code, and I might go back to the main code base, or maybe I'll look at the inventory. So yeah, I have these comments. If the command was inventory, then see if inventory hash exists in the data store corresponding to the inventory type. So we have a data store where we try and collect and index all these different messages from a Bitcoin node, and we get an inventory message. We check the hash of each inventory message to see if we contain it. And we ask for the inventory from the source node if it's not present in our stores, and we try and get the blocks for orphan blocks if we don't have them. So we can see that happen here. We have vinv, it's uninitialized. We read using this vreceive stream. Just a couple different angle brackets say that we're reading into vinv. And we open the transaction DB in read mode. That's what we had before. We used to have this transaction DB in the code, which contains all the transactions. And then for each inventory, we could disregard this. I was understanding that INV stands for inventory. But yeah, we add this inventory to our known inventory, and then we check if we already have right in the transaction DB. This is a lot closer to natural language than the current modern version of Bitcoin. We print that we got the inventory. Again, these are the original logs. I didn't really change much here. And yeah, if we didn't already have it, then we ask for it. Pretty straightforward. Else, if the message is a block, and we found, if we have these things called orphan blocks, which are blocks without parents. So if you give me a block, and I say I don't have the previous block, in my data store, then that is an orphan. So this code is saying, hey, if
How would that happen though?
if your node just sent me something newer than I was expecting.
Oh, okay.
Yeah, something happened and we're just out of sync. You don't know what to send me, so you sent me a block that I didn't have the previous one of, but you thought maybe that I did. But yeah, if we do have an orphan block and you were to send me an inventory message, again, inventory message is just a hash and then a message type. And the message type is going to say this hash represents a block or a transaction. If it's found in the orphan blocks, then I will push a message to you saying, hey, I want to get the blocks, and I will get the root of the orphan from you. And this is a different function that tries to figure out. I think the last place that I had, oh yeah, reorgs. This was also a thing. Sometimes the blockchain can change. The newest block isn't always final.
The most recent.
Yeah, but just because the block gets confirmed doesn't mean it can't be reorged. So you could have 2 block reorgs where you had 2 blocks of transactions and another miner was doing some nonsense, and they published 2 other blocks and a 3rd block. And what happens when they do that is they remove the latest 2 blocks in favor of the miner's 3 blocks with more work that was attributed to them.
Right, because it's always the chain with more work.
Right, exactly. The most work chain. So yeah, the reorgs are essentially when another miner, or when there's 2 competing miners, and one miner tries to invalidate the blocks of the other miner by putting more work into them. So yeah, some of these orphans can be caused by reorgs as well.
By putting more work into them.
Yeah, although the original.
So they can choose how much work goes into each block?
You can, but it's very hard. you know, to the problem gets like a lot harder if instead of just going for the difficulty that the blockchain is at, then you have to go. But yeah, you can target a difficulty. And you can mine, or you can put more work into a block than it is necessary. And that also happens like randomly. Sometimes you will hit like a hash that's value is like such a small portion of the probability of happening that they're called like super blocks, I think, or something like that. Yeah, sometimes it just happens by chance. All this is probabilistic. But yeah, so reorgs can happen, work can happen. Although in this first version of the code, it doesn't go off most work. It goes off like longest length. And that's a problem because like, anyone could forge like blockchain, right? If I'm making a blockchain and I put like, this is block 1 with these transactions, this is block 2 with these transactions, and I put some like hash power to it. Let's say you can measure the hash power
currently at the very moment.
Right, and like let's say I put one unit of hash power in this block, and 1 unit in this block, and 1 unit of this block, and you put 100,000 in the first block. In this version of the code, my blockchain would get taken over yours because mine was longer. And that's like a bug. It should be the miner who spends the most energy because it means they cared the most, right? They have the most at stake of like it not being correct. Right. But yeah, this code has a whole bunch of bugs in the V1 version, but it's still a pretty good code base, and no one, I don't think, lost a significant amount of money from a bug on Bitcoin. That's to my knowledge at least. Yeah, you have all these other different commands you can make, like get data, get blocks, transaction. Maybe I'll look at transaction. So again, these kind of things, when it's just like the data name, like transaction, means they're trying to give us some data. So we have this thing called the work queue. A lot of programming is you reading variables and not knowing what it does immediately. You have to look at the rest of the code and see where this variable name fits into the context of the whole function. But you get this work queue. You have this, make a message from this receive stream. You create a transaction, which is empty, there's nothing in here, and you read in from a receive stream into a transaction. So, this is a receive stream is almost like a shared box between us, let's say, where we pass messages to each other. So you might put some messages in the box, but and this is the mailbox, until I use these 2 arrows, I haven't checked my mailbox yet. But, right, exactly, yeah. So you could say that you could send data and you could put the flag up and I could see that there's data waiting for me, but I could read it, at my own discretion. So this vReceive is, a stream from you of information. And whenever I want to read it, I can use these 2 angle brackets and say, all right, I'm expecting a transaction from Mars. In fact, he told me that he's giving me a transaction in this, string command transaction. So I should be able to go and pull out something from our mailbox or from the receive stream that can fit within a transaction. Because I made this transaction first, and then I'm trying to stuff the information of a transaction into the transaction I made. So then I make an inventory message with this transaction, and I get hash. And this is nice because even though you gave me a whole transaction, I am keeping track of what I have and what I don't have using the inventory hashes. So you gave me a whole transaction. I put that whole transaction, into the data structure of a transaction, and I just got the hash of the transaction. I made it into this inventory, object.
It can be pulled.
Right. It's a way for me to like easily reference.
Yeah, it's like tabbing
Yeah, exactly. Yeah. It's a reference to the hash. I don't need I don't need the whole transaction.
You need the whole transaction just to get that little piece of.
Right. Exactly. So I put it into inventory instead, and I check if I have your transaction using the inventory, which just contains the hash and whether it's a transaction or a block. So you, again, just to go over where we are right now, you gave me a transaction. I took your transaction and I just got the hash of it, and I'm checking if I have the hash of your transaction. Well, first I'm adding it to my inventory that's known, and then I'll have to accept the transaction. And here is actually where I might check if I already have it. And there's a couple different checks that I make before.
Throughout the process.
Right, of accepting a transaction.
Of course, right.
So accept transaction is a whole different function with a whole different functionality. But after I've accepted your transaction, there's some other processing I do. So I'll add your transaction to my wallet if like the transaction is something I can spend, for example. Another thing I do when you give me a transaction is I try and relay the transaction, to other people. And I get a.
So like when you went to the accept transaction thing, that box came up, right?
Yeah.
So I was looking at the numbering on the code lines, I guess. I don't know.
Yeah.
So he already established what accepting a transaction is way up there in 700 or whatever.
Right.
Right. And so you're just referencing it here.
Yeah. This is just a window to the function above this part.
Gotcha. Just wanted to make sense of that as we were going through what I'm looking at. Cool. It makes sense to me. I got it.
Yeah, and then all my initial comments, saying that things are weird. You could actually see when sometimes it shows the year. See, 3 years ago. F client. I do know what F client is now. It's a light transaction, but I didn't know back then, or a lightweight client. But yeah. So after I've accepted your transaction, I add it to the wallet if it's mine. I'll relay the transaction that you told me about to other people, and then if I erase the inventory from the map already asked for, if it was in there. Because we just got to, I don't know why, put this question, but add the inventory hash to work queue. I forget what work queue is, but I guess we're going to go to it here. I look through the work queue. Actually, let's see what Satoshi put. Recursively process any orphan transactions that depend on this one. So yeah, he was thinking a lot about like orphan transactions. Again, like you have these things called like reorgs, which sometimes rearrange the blocks.
Is that just because he didn't like expect for there to be a lot of nodes connecting to each other or something? Like what? How was he so focused on orphan transactions?
Because he wanted to make sure that like no one gets out of sync with what the consensus state should be. So if you weren't handling these cases correctly, then people could have like different versions of the blockchain and arbitrarily like ignore transactions from other people without the concept that, hey, this blockchain, it isn't permanent, it can change, and sometimes you'll get data that seems inconsistent, so you need to go and handle it when that happens. That's what these orphan blocks are. Look through all elements of work queue. Yeah, he just does things with orphans here. I like how they're called orphans. It's pretty funny. We could look at another data passing. Let's see what else we have here. Check these orders. I don't think are in the current code. I think this is used for something else. Reply. Let's look at get blocks. Get blocks, you had this thing called like a block locator. These are like, variables that you use that help you manage the data, find data and manage it. You have this thing called a hash stop. I don't know. I have to look at what this was.
Is the hash of the transaction you want to retrieve?
Yeah, so again, we receive that's like your mailbox, and I'm putting it into locator and into hash stop. So I use the data stream to deserialize the locator, and then I use the vreceive buffer to deserialize into hash stop. Okay, yeah. So again, I take what's in your mailbox and I read it, these locator and hash stop. I know that whatever you're sending me fits into these data types because you gave me this command, get blocks, before I started reading the contents of the things in the mailbox. Yeah. Locator, I get the block index of this locator. Let's see what Satoshi had to say. Find the first block the caller has in the main chain. Okay, so when I receive a get blocks from you, because again, this is a process message, this means I'm processing all these messages and it came to me. So if you gave me a get blocks, that means that you're asking for blocks from me.
Right.
Yeah, so I took, and when you were asking me for it, the two things that you had to give me were this locator and this hash stop. And then with that locator, I was able to get a block index. Yeah, which means the first block that the caller, which is you,
Right.
has in my main chain.
On your main chain.
Right.
Okay.
Yeah, so you give me something, you're like, here, you said, hey, I want some blocks. So you said, get blocks.
Right.
But you also gave me information for a locator, which is supposed to be a reference that I could use to find your latest block in my main chain,
Right.
to see where we differ, or like to see what you need.
Of course, right.
So the locator is essentially a way for me to locate where you are in my more expansive data set.
And so, okay, I think I understand the concept more of the orphan blocks.
Yeah.
Right? That would be like if I can't find it at all, you're asking me for information that I don't even have.
Like an orphan block would be, you give me a block, but I don't see its like parent. I don't see the previous block in my own data stores. So I have to store it as an orphan until you are able to give me more information.
Gotcha. I don't know, maybe I'm fixated on the name.
But yeah, orphan is treating like a previous block as the parent of a subsequent block.
Of course.
Yeah, so it's just
I'm
saying.
just trying to figure out like how your node. Okay, well, I guess later on, once I give you more information on that block,
Right.
you'll be able to link it to.
Whatever the correct chain is.
Later on, right.
Yeah. And again, I can see orphans happening because of like chain reorgs. You know, like if let's say you had a block 1 and a block 2, and I had a block 1A and block 2A. But let's say we are both working off, block 1 and block 2, and I guess this is when I have a different set of blocks. But let's say both of these chains are valid with equal work, and then someone makes block 3, and then actually, I know that this example is getting more complicated, but yeah, let's say me and my friend, we're both on block 1A and block 2A, and then there's another node who's not connected to us, connected to another miner, and he was on block 1 and then on block 2. And we're all waiting for a third block. And let's say this node gets a block 3 from his miner friend. And after he got the block 3, then he decided to connect to us. And he's like, hey everyone, this is block 3. And then you and me, we're using block 1A and block 2A. So when he gives us block 3, we're expecting block 3A. But his block 3 connects to block 2. And we don't have block 2. So we're going to just put this into an orphan block until we can legitimize this chain and see that this has more work, or it's longer than the chains that we have. It really should be more work. But
and then if it is, you would just get rid of the chains you have.
Right, yeah, and then
just go with his chain.
Right, I'd have to take that other chain as the true chain, because
you guys would all now have block 1, 2, and 3 instead of 1A, 2A, 3A.
Right.
Gotcha.
But, and then that'd be a reorg, so like, these blocks would disappear and get replaced with these blocks, which happen in Bitcoin sometimes. So reorgs or reorganizations aren't very common. There's like a whole website for it.
Yeah, because every 10 minutes is when the blocks are confirmed, right? So like that would take like 20 minutes before a reorg would happen?
Yeah, so it doesn't have to be every 10 minutes. It's like probabilistic.
10,
it could be 1 minute, like it's all probabilistic. On average, it's supposed to take 10 minutes. Yeah, but like someone could take 1 minute. Another way that you could have a block produce more quickly is if I had like a boon of hash power. Like if someone gave me 100,000 more ASICs than I had before, and I'm like swamping the whole competition, then the difficulty hasn't adjusted to like my hash power yet. So what I'd do is I could start making a whole bunch of quick blocks.
Right.
But after I think it's 2014 blocks or something, it tries to readjust the difficulty. So if I did it too fast, then it would be like, hey, we have to make the difficulty a lot higher, since we have to make it harder for the person with the most hash power in the network, pretty much.
So you can't just turn on bunch of computers all at once.
Right. Exactly. And say I'm gonna dominate all the
Here we go. Turn it on.
Right, exactly.
Okay.
You can't do that forever. Yeah, you will have a difficulty adjustment eventually that says no. We're gonna make it hard for the person with the most hash power. So even if you dominate, if you have 99% of the hash power, the Bitcoin consensus algorithm still limits you in how fast you should be able to produce blocks over time. Eventually, it gets there. But yeah, I was gonna look at some reorganizations since we were talking about reorganizations.
I'm sorry. When you said eventually, like, how long is eventually?
However long it takes me with all the new hash power to get 2014 blocks, I think it is.
Okay.
So if let's say I had a whole bunch of more hash power than I did before, and I solved those 2014 blocks in like 10 minutes, then that would be the duration of time before the difficulty adjustment happens. I think it's that number, and I could double check. This has difficulty adjustments as well. So let's see, is it 2014? Where's this from? Hold on, transaction clone. Oh, this is the current Bitcoin. I want this version of Bitcoin. It's, I think it's not 2014.
So I guess in the future, it would adjust the difficulty faster, right? Because you're getting to 2014 quicker.
Yeah.
Right.
Yeah. So you do. There's a notion of time within every node, and every node can see how fast you complete a certain set of blocks. So when a difficulty period ends.
Minutes. It's a calculation.
Right, but I mean they also keep track of minutes as well. So
Okay.
So there is an actual clock that each node uses.
Right. Okay.
Yeah, and if you do something too fast with respect to everyone's clock, then everyone will all agree that you need a difficulty adjustment as the predominant miner on the network, or even if it was consensus. But yeah, getting a little way from
Yeah. Okay. That's
the period. No, it's good. But I wanted to see what the period was because maybe it's not. Was it? Let me see. Get next work required. I want to see what this n interval of blocks. Oh, yeah, he had some calculations on when the difficulty should be adjusted. Interval comes out to about 2016.
26.
Yeah, I think that's the number of blocks. How many blocks Satoshi would like? Mine within a 2-week interval, which should be about a block every 10 minutes. So yeah, did I say 2014? Yeah, I meant 2016. Yeah, he has these things 2 weeks, and he made sure. Yeah, and this is his calculation for difficulty adjustments. Again, it's away from peer messaging, but why stay at peer messaging? Why not just explore?
So it would take roughly about 2 weeks for the difficulty to adjust.
Yeah.
If you're doing some fuck shit.
Yeah, exactly. So if a miner comes in and he tries to mine blocks too fast, then he will face a difficulty adjustment pretty quickly. And yeah, this is testament to that. He has these end target spacings. He has all these kind of magic numbers. But you could kind of figure out.
See, that's just shit that. Oh, dude.
Yeah.
As someone who likes numerology and shit, like.
Yeah.
The reasons behind all these numbers.
Yeah.
So I'm looking at the 5s.
Yeah, because he multiplied all this.
It's literally like 5, 6, 6, 6. Like when you look at the 1 and the 4 is a 5, the 2 and the 5.
Okay, yeah. If you're add each digit.
Yeah, so it's interesting.
Yeah, and it's also 2 weeks, 60 seconds, and 60 minutes. That makes hours times 24 hours.
24 hours.
Yeah, times 14.
Days,
Yeah, and then that's his desired goal of 2 weeks, and he even commented 2 weeks. Have the Satoshi start, Satoshi end. But yeah, this is his target time span. Yeah, well, 2 weeks. Yeah,
if I can get a Satoshi interview, I'll be so happy.
Yeah, well, all the numbers worked out so that there's only going to be 21 million, right? Which was also a very nice property. Yeah, he had this target spacing, which was 600 seconds, 10 minutes, and then he had this n interval, and then he had all these other calculations that related to this. Yeah, when I put some calculations again, a little away from pure messaging, but this is might be more interesting. So why not explore that? But yeah, we were talking about reorgs. So I wanted to show you how many reorgs have taken place. There's a site that has a live number of reorgs. I don't know if it's this one. longest chain. Your node will deactivate blocks. Yeah, this says the longest chain, but they do correct themselves, and I think it does say most work. Except as the valid version of the blockchain is a solution. What is the longest chain? In short, to add a new block, the most effort to build. Yeah. So again, this wasn't always the case. It was a bug in the first version. But yeah, the longest chain here is defined as the one with the most work. And this is a pretty good website if you ever, I don't know if you
really cool,
looked at it. Learn Me a Bitcoin. Yeah, he has things about chain reorgs, and I think he used to have data on this. Okay, here we go. He has up-to-date data. These reorgs don't happen very often, as you can see. One in March 2023, one in May, a couple June, July, August, October, November, and 2 in November, which is like it's an uncommon event. These are one block reorgs, so you typically don't get 2 blocks. It's possible, it just doesn't happen. Actual reorgs, avoided reorganizations. We heard about a change that could become, but our active chain at the time continued as longest. Okay. So these are when other chains come close, but only 15 reorgs.
Right, that's crazy.
Yeah, since December 2016. So when you make a payment, it's pretty final. Out of how many blocks we have? 81,000. Or no, this is 800.
818,000.
Yeah, and we still only have 15 reorgs.
But it seems like most of them happened this year.
A lot of them have been happening, this year. Why? Because with inscriptions,
inscriptions and
shit. You have,
That's crazy.
Yeah, people doing, these high fee transactions.
Look at you, Professor X.
Yeah. Yeah, and all the miners, they go, Professor X. Yeah, so these are reorgs. Pretty interesting stuff. Let's see, I'm gonna see if I can go back into the peer messaging stuff. I mean, by the way, if there's something else that interests you, we could go to whatever. But yeah, we could do it, on mining. This was a little bit on the mining stuff.
All interests me, all of it.
Yeah. I undo this. But yeah, we're back at get blocks. But yeah, like we were saying with get blocks, you put something in my mailbox. You say, hey, you want a block, and you give me this locator and this hash stop. I take your locator, I see where it is on my main chain. If the first block of the main chain was found, so p index is this the reference to the block that your latest one is on my chain. So I say if if I have p index, so whenever you see this if, and it's just a variable in the middle, it's just like if something's there. If I have p index, then I will set the block reference to the next block. And then I log your request to me, and then I say for every block from the block after the one that you said you had, all the way onward, I will get the block hash, and I will see if the block hash equals the hash stop. So before you ask for blocks from me, I'm giving you a whole bunch of inventory messages, right? Inventory messages don't have the complete data of the blocks. They just they just have the hashes. Right. So but you could see which things lead into what. So you can see what the end is of what you want.
So I could see what the end of the hash on the block that I want is.
Right.
And then what the beginning of
the
first hash of the next block.
Well, yeah, the beginning range is the locator that you gave me.
Right.
And I just see now, that the hash stop is the place that you want to end.
And look within these parameters.
Right. And you're asking me for them because you said you don't have them.
Of course.
I give you some inventory. Right. You're like, hey, I need
I need you to check this out for me. Look between here and here.
Right.
Kind of like a library lady. How you like, hey, I need to go get this book. And she's like, oh, I got you. And she runs back and go get it for you.
Exactly. Yeah, like a librarian.
Yeah. See, I'm thinking of illustrations and things that I can use when I'm doing the Bitcoin 101 thing. All these different things, I'm putting them into real world
Yeah, scenarios. I think that's how it works best. Like these analogies, they do have real world analogs to them, and it only makes sense to try and.
Right, because that's
Yeah.
how I think about it, right? Like a library of transactions, and then like the locator is literally locating.
Yeah.
Transactions, right?
Okay, sorry, I wasn't even looking at any of the comments when I was looking through the code.
Someone's here?
Oh, no, not someone here. I was citing the Twitch comments.
Oh, gotcha.
Yeah, I feel bad. Are those, I see Prav, I don't know if he's still in here, but he said, are those comments from Satoshi? The comments on this code base, if it's a loose comment, it's mine. If there's like a Satoshi start and Satoshi end, then whatever's in the middle is from Satoshi. But I tried to go over the code base and comment every single line for myself as part of this original code base.
So everyone kind of does their comments differently.
Yeah, everyone comments differently. This like commenting every line is only good for learning. Typically you don't want too many comments in your code. You don't want every line to have a comment it shouldn't need. But to make sure that I read every single line and understood. I had some semblance. Yeah, I said I need to go through every single line. I need to comment every line.
How long did it take you to do all that?
A couple months maybe. And again, this was like in 2020. It was like 3 years ago, right? So when we see my comments, 3 years ago. So it was a couple months, and I was passionate about it, so I was learning more. But it's been a while since I looked back at my comments, and I could probably fix up a lot of the comments or clear up some of the things I didn't understand back then. But yeah,
is this something you can publish?
Oh, it is. This is on GitHub. This version of the code with my comments on it.
Comments.
Yeah, yeah. It's maybe it's not the easiest to find, but I could give it to you later if you're ever interested in looking through the lines of code.
Once I start learning code, like that's the thing I like to learn as I'm like doing. I learn more hands on.
Yeah.
So like that's perfect. That's a
Yeah, but it's applicable when you're understanding how things work. Another thing that's good is when you read every line, like you could see what the strengths and weaknesses of a system are.
Oh,
right? Yeah. You can see if there's a bug too.
You know how to read,
yeah. And the more people who know how to read, the more decentralized Bitcoin becomes in terms of people who
I
could.
love this, and so I like seeing it. Because even when I'm explaining it to people, like that's one of the things that I figured out that I kind of realized like my skill sets were. Be able to like break this down into like layman's terms, in the way that I can think about it. And people, they actually get it. They actually understand it. And you're like, cool. Because I didn't think I understood it. So I'm explaining it, and I'm like, oh shit. Okay, cool. I do understand this in a way. So it's good to get more advanced.
Yeah, and I feel like people like you are able to take information like this and condense it into real world scenarios and like analogies and stuff like that. It's very, very helpful. I try to do it, but again, like I also want to keep it at the technical level. So,
of course, right?
Yeah, I'm trying to make analogies for sections of code, and it sometimes is really hard. Like trying to make an analogy for this part. But I think as we go on, I can like get a better sense of how to do it.
Right.
But yeah, so. Going back to you asking me for blocks, you gave me a locator of where to find the block, the start of the block that you wanted, and you gave me this hash stop that says this is the last hash of the block that you need, and then I will make this for loop that will iterate through every single block from the block locator you gave me until this hash stop, and then I actually break out of the loop when I've reached a hash stop. And if I haven't reached the hash stop yet, then I will actually go and make an inventory message with that block, and then I will send it to you. Okay, but I'm only sending you the inventory. If the inventory is not already known too. Yeah, so I'm only sending you the inventory. So actually, this scenario doesn't happen with me just sending you an inventory. This probably happened because you received some block that was far ahead, and you just didn't know where it belonged. So you probably gave that to me as a hash stop, and you gave me your latest block. So, this is, I guess, if you got a block that was like an orphan, but you thought that maybe I had the parent blocks before it, so you made the get blocks request with your block, as found with the locator, and this hash stop of this unfamiliar block to you.
Right.
And you're just asking me if I know anything in between. And if I do, I will get an inventory of the hash of it and I'll send it to you.
Right. And if you don't, if the inventory is not already in the known set, then
oh yeah, the known two. There's a set inventory known and a known two set that he had. I don't remember. Here, let's look at Satoshi's comment. Returns true if it wasn't already contained in the set. Okay, not super. Inventory is made as a block message, indicated as message block, and the block hash is attached to inventory as well. Okay, set inventory 2. Okay, yeah, we can read my comments and see what I understood back then. If the inventory is not already in the known 2 set, if it is the... Huh?
I honestly don't remember what's in it.
Okay, yeah. Yeah, so I committed that commit long after I started making my changes. So I didn't remember everything that I was annotating. I was just I just want to save it somewhere, so I made a commit on GitHub. But yeah, my comments, if the inventory is not already in the known 2 set, if it's the first time this inventory is being added to set 2, erase it from set 1 if present, so we can add it back again. Erase the inventory for the known inventory, add the inventory as the... I don't know what it's doing here, to be honest. Inventory to send. Oh, I know that we're sending something to be sent. Where do we populate this set inventory to? Let's see if send the rest of the chain. Okay. See, Satoshi is very helpful. Send the rest of the chain. Great.
So all the rest of the previous chain.
Yeah, or from your hash stop.
The hash stop.
Yeah, exactly. Send everything before the hash stop, from what you said you had last, and to the hash stop. That's what you wanted.
Together.
Yeah. And you took the initiative by sending me a get blocks command
right.
to give you that. And again, but this is I actually like this in the fact that it's a pretty short function. It's pretty easy to read through. Again, it's very, very hard to read through the current code. P from set inventory known to. Yeah, I don't remember the exact thing. I wasn't too descriptive here. It's the first time. I don't know what the set 2 was used for. I can't remember. And if you want to look at the modern version of get blocks of how nodes handle requests, then we can look back at Bitcoin. But again, this is just so much. Get blocks, peer-to-peer. Oh. So yeah. Now instead of doing the straight strings, they use these constants instead. And I think I should find it. Oh.
Instead of strings, they used constants.
Yeah, that just point to these strings. So it's still the same strings, but yeah, they don't. You don't want to put the quotation mark blah blah with it. If you have a constant, you could use the same constant again and again all over your code. And then when you want to change, the value of that constant, you change it one place and all the other places. Yeah, it'll propagate. But yeah, here is where we handle where. Isn't net processing? Get blocks. This is not what I'm looking for. I don't think it's definitely not here. Okay, here it is, net processing. So again, comparatively, let's minimize this. This is 3965 to 4030. I guess it's not that long. But it's from here to there. And it's pretty similar in the modern version too, right? I mean, we're looking at the old version. This is the modern version. You still use a locator. You still have a hash stop. I'm still taking from this vreceive as the mailbox. You have an extra log here that you didn't have in the old version, but a lot of things are.
Log. What is the log?
Get blocks locator size. You just give us you give more information to the user.
Okay.
And then we have this. Let's read what this is. This was written by Matt Carollo around 7 years ago. We might have announced the currently being connected tip using a compact block, which resulted in the peer sending a get blocks request, which we would otherwise respond to without the new block. To avoid the situation, we simply verify that we are on our best chain now. This is super overkill, but we handle it better for get headers requests, and there are no known nodes which support compact blocks, but still use get blocks to request blocks. Compact compact blocks are something that were introduced in newer versions of Bitcoin. It's part of like, again, this language between Bitcoin nodes. He was saying older versions don't have compact blocks. Yeah, compact blocks are essentially a way to like share information that you have on blocks without it being as bare as an inventory, but without it having too much information as a block. So like someone, in the Bitcoin developer community said, inventory doesn't give me enough information and a whole block is way too much. Let's make something new in the middle. And that's what a compact block is. And it gives you hashes related to the block, but it also gives you hashes related to the transactions in the block without actually giving all the transactions itself.
Right.
So that's what these
How
like.
do you choose the information that goes into the compact block?
It's like defined in the code, and it is a smaller subset of the information that
So
goes.
like one block might have what, like 5 compact blocks in it?
Oh, I don't know. They're like completely separate
It's
entities.
completely separate things.
Yeah,
Gotcha.
compact blocks have nothing to do with like the blockchain,
Right.
like necessarily. It's only something that's used in pure messaging.
Gotcha.
Just like the inventories are just used in like pure messaging to sync between us.
Right.
And it's essentially, me taking a block and trying to see relevant portions that I think you might be interested in.
Right.
So a compact block is like the transaction ID and some of the transaction IDs and the block hash. I could see if I can find a compact block definition here too. I just need to find the type for a compact block.
And I feel like when I heard compact block, I thought of Mark.
Yeah,
See, block was high as wall. I was like, oh shit, here we go.
yeah, like hasher. I want to show you what a compact block is. I'm trying to find the type here. That's it. I think it's like compact block. Here we go. C block, header, and short transaction IDs. So this is a compact block. Compact block has like these short transaction IDs. It has like the nonce. So these are what we call like private fields. You can't access them directly, but you can access them from like within the data structure. But yeah, it's a whole bunch of like the transaction IDs that are part of a block and these pre-filled transactions. And again, it's a subset of what's actually in a block. These are serialization methods. I know I'm like all over just explaining random things,
No,
but
yeah,
yeah, you see these serialized messages a lot in the Bitcoin code base, and these are very important because they describe how things should be written into bytes and read from bytes. So sent over the wire is just like zeros and ones, right?
okay.
So like these type of serialized methods are like the algorithms of how you decompose those bytes into like something more structured, or taking the more structured data and putting it into bytes.
Into bytes, yeah.
Yeah, so you have like these
So
formatters.
What are the nonces? What do they do?
Yeah, so
That's just a unit?
no. So this is a compact block, and it has a subset of data from the block. The block, sorry, I say a comment on Twitch. I was looking at the code today to figure out how the initial difficulty was set differently for mainnet and reg test, and found out it's a parameter to create Genesis block in kernel chainstate.cpp in a field called nbits, which I thought was interesting. Yeah, it is an nbits. We can see that in this first version as well. Nbits. See, you have these. Oh, not here. But yeah, so in this version is actually pretty simple because you don't have that many functions in this main file. But yeah, nbits is still relevant today. When you get the work required, you would get it in these nbits, and you could see initial work. In fact, there was a whole class, I think, for where is it? There's yes, nbit. Oh yeah. Yep. There we go. Somewhere. Here we go. This is what I was looking for. Bool Bitcoin miner. Wait, is this what I'm looking for? Yes. You had a function that was a Bitcoin miner within the Bitcoin core source, and this is where you could find all of the information related to Bitcoin mining in the first versions of Bitcoin. In this Bitcoin miner function, and you can see it. There's a while loop that just goes on forever. It sleeps. We could see it do some work somewhere. But it's very easy to look through all this stuff. Here we go. For end this while loop, this is where it does the hashing, and then literally does a less than an equal sign for the hash target, which I think is pretty cool. It's very simple, and that's why I like the original code base, because it's just so much easier to understand. In fact, yeah, I could pull up the original source code on the repo. Sorry, I'm getting mixed up with the screens. That's not what I want to do. Oh boy. I'm trying to get a link for you. Here we go. Safari. But yeah, this version of Bitcoin, this is the actual repo off GitHub. But yeah, if you go early enough, you could find the first commits. I have this page bookmarked, but the first commit gets farther and farther from the front. But this, that link used to be able to point me to the first commit. But yeah, we could see the first commit that they put on GitHub here. And this is the same code base that I've commented and used. And if you look at main.cpp, yeah, Bitcoin miner. Yeah, I was just showing how the first Bitcoin miner was just a function in this main file of Bitcoin.
The first Bitcoin miner was just a function.
Yeah, now we have dedicated programs for mining Bitcoin, but back then it was all bundled in this one. Most of the logic was bundled in this one file, and the Bitcoin miner was some lines of code. See, it's really not that much. It's a couple hundred lines. Yeah, this is a miner. That's it.
Wow.
Nice and compact.
It's insane to think about.
Yeah, anyone could make a miner pretty easily. All right, but I guess I'll go back to core. I know the peer messages. I mean, but yeah, compact blocks. Sorry, I went from compact blocks to the mining. Yeah.
There's no mining code.
Yeah, it's pretty crazy. Let's see. The bug you found 30 minutes ago, is it like Superman 3 or Office Space? I don't remember Superman 3, and I don't remember Office Space much, but I remember I liked it. Gimbal lock, I see. I figured out that for the first difficult epoch, you could mine a block in 4.3 seconds if you had 1 gigahash. Yeah, and that's what I was talking about with Mars earlier, that with enough hash rate, you could zoom through all these blocks. Reg test has an actual difficulty, but it's a billion times less difficult than mainnets. Yeah, I've seen that as well. When you if you use Bitcoin Core and reg test, just locally, and you generate some blocks, and you put something like 100,000, it takes some time to actually fulfill those blocks. So it's not super trivial. But yeah, it does do some calculations behind it. But yeah, going back to the short block, or compact blocks, I mean. But yeah, these are compact blocks. Oh, you're asking about the nonce. That's how going to mining. In fact, this is a great opportunity to go back to that code base that I had here. Maybe I'll just do one straight from GitHub. So, Bitcoin miners, right? Where's the part that I'm looking for? This is all mining is. You're trying to find a number, right? You hash your block full of transactions, and then you include something called a nonce within the hash that you already have, and then you hash it all together, and you're hoping to get a number that is below a certain threshold. or maybe I should, step back a couple steps. A hash can be represented as like a number.
Right.
So every hash is like, you could also conversely think of it as a number.
Right.
And when you hash something, you get in hexadecimal, like you get like a long sequence of like letters, right? A, B, whatever. But at the end of the day, it could be represented as a number.
Right.
And when you're mining,
Because the letters are still numbers.
right, exactly, because hexadecimal, still resolves back to bits and bytes can always be converted back to numbers. So when you're mining, you're actually hashing a bundle of transactions, and not only that, but you're hashing something else that you include in the bundle of transactions called a nonce. And after you hash the bundle of transactions with the nonce, you get the block hash. Now the block hash will not be accepted by all of the Bitcoin nodes on the network unless the block hash is below the consensus agreed difficulty. But if my hash was too high to be under the difficulty, then I usually don't change the transactions in my block, although I can. Instead, what I do is I change the nonce. So I can keep the same set of transactions, and I can change this arbitrary piece of data. So
that makes it easier for you to hash it.
Or it gives me more options. I'm trying to think of like a good analogy.
Because you're saying that, so the hash rate has to be less than the difficulty. So if it's more than the difficulty, it would have to adjust.
Yeah, but the only way that you can adjust is through this nonce. That's not true. You could adjust in other ways. You could switch up the transactions in your block as well. You could make subsets of the transactions. There's a lot of different things you could do to change the block hash and stuff a valid block. But the first
change your block hash instead of what? Instead of a valid block?
Oh no, yeah. I said there's a lot of ways you can make a valid block, but like that are constructed with different transactions.
Okay, that makes sense.
So yeah, the goal of mining is you take a bundle of transactions.
Right. So you could, like, if the difficulty is too hard to basically mine the block that you have, you could change that block.
Yes. And
prior to the current chain being confirmed at the moment, I guess.
Yes. Yeah. Exactly. While the next block has not been confirmed.
Has not been confirmed.
Yeah,
yet.
you could work off the previous.
It's too hard. Fuck it. I'm gonna try this one over here.
Right. Yeah. Yeah. Exactly.
So you can just keep doing that until you finally
right.
get it.
Yeah. So if you hashed a block and that hash was not low enough to what you wanted, you could switch around the transactions in the block and then get a different hash.
The nonce allows you to give different options on how you want to go.
Yeah, exactly. Well, the nonce allows you to make a change that gives you a different block hash without changing the transaction inside. And I see Gimbal Lock had some comments here. He said, my analogy for mining is trying all the combos of a combo lock. That's you're trying to guess something.
Right.
And he also said, but you only want a solution where the first digit of the combo is 0. So
right.
Yeah,
right.
so you're making a whole bunch of guesses.
But the first one is always 0, and you're always like trying to figure.
Right, exactly. So you're trying to tweak something, but
think of it like I don't know if you ever use a camera in like manual mode, but there's like shutter, aperture speed, ISO, and like the ability to adjust your aperture made digital cameras so popular because like it gave you the ability to basically have different options.
Yeah.
What you want.
Yeah.
There's not enough.
But yeah, sometimes you want the same picture, but you just want different parameters, right? To reach a goal, right?
To get where you want to get.
Yeah, so that's what the nonce is. It's essentially something just so you could change the block hash without changing anything else.
Right. Cool. I get it. It's like an adjustment now.
Yeah. And also what's interesting is, these SHA-256 hashes, typically it's not just like one, it happens twice. So things are like doubly hashed. A lot of people don't know that, you doubly hash things. So you take
the first hash looks like that, the second hash.
Yeah, so this is taking the block, it's taking, n block 0, and then it's doing this like hash and putting it into temp hash 1, I'm pretty sure it was doing. And then you take temp hash 1, n blocks 1, and then you put it into the actual hash.
Right.
Yeah.
Makes sense.
And why did they have n blocks 1 and 2? I can't remember. Let's go back to my code to see. Like it's enough space. Okay, yeah, it's just space. Temp block, and it returns the number of 64-byte groupings needed. Like it's enough space for temp 1 hash, and it returns the number of 64 bytes. Okay, it's just signifying the space that that hash would take, I'm pretty sure. But yeah, I don't know, nice little detour into mining. But, and let's see if there's anything else in pure mining we could look at, or in the pure messages. Okay, compact blocks, I might like ditch that for now. But yeah, that's what the nonce is. Hopefully, you know, my explanation helped with something. Going back a couple times to see. Okay, we're looking at compact blocks. In fact, we could see, so this compact block did not exist in the first versions of Bitcoin. So if you like, you know, look for it, it's not here. So this was a newly introduced peer message, you know, compared to the first version of Bitcoin. Here, sorry, just gonna make sure my chat is still up so I could see. Yeah, so the compact block. Why don't we look at what that is? So when we received the message for compact block, so you tell me something's in my mailbox, and you say, hey, it's like, I'm giving you a compact block. I'm like, okay. I do a check. What is this check for? Chain manager, block manager, and I do some loading. Okay, so I guess I'm loading some blocks up. I don't really know what this is doing here. Okay, but then again, this is your mailbox. I'm receiving your compact block into this data structure. Receive new header is equal to false. I'm just initializing this. Block hash is equal to the compact block header that you gave me, and I get the hash of it. What do I do with this compact block? I haven't really looked too much into compact blocks, so I'm curious. I get the previous block index by looking up the block index of your compact block that you gave me. And then if I don't have the previous block, and I'm not in the initial download, then I hate these like, yeah, I hate this like, yeah, terminology. Yeah, IC Prof says always double hash, rinse and repeat like shampoo. Yes, double hash is, yeah. I mean, it's not like a rule of thumb kind of thing.
So you can choose whether you want a double hash.
No. When it comes to mining, there is you do have to do that double hash. Right. A lot of things in Bitcoin, a lot of people think it's like one SHA-256 hash, but there's actually like, you know, double hashing, more entropy maybe.
And that's just for extra security.
Yeah, I guess. It's kind of an arbitrary, you know, decision. I think there was a Bitcoin wiki entry about that, like why there's double hashing.
Why double hash?
Yeah, what are the benefits of it? Let's see if another detour, but you know, things are best with detours.
No, I love it. That's how you learn.
Yeah, let's see. Why does Bitcoin double hash? Is this okay? This might be good. Why does Bitcoin? Is double SHA-256 the best choice for Bitcoin? Since the initial release of Bitcoin is January 2009, the designer had these NIST hash functions as available options. You could use SHA-1, SHA-256, SHA-512. The main difference between SHA-256 and 512 is the target CPU. SHA-256 is designed for 32-bit CPUs, and SHA-512 is designed for 64-bit CPUs. That makes a huge difference in the target CPUs. One can argue that the designer wanted protection against the length extension attacks. However, SHA-512 and 256, which has the same preimage, I just wanted a simple answer. The obvious choice can be considered as the speed. SHA-512, according to Blake 2 site, is 50% faster than SHA-256. But this doesn't explain the double hashing. Yeah. SHA-256 is slower, which is a good property when it comes to...
256 is slower, 512 is faster.
Right.
Gotcha.
But that's a good property when it comes to mining. But the big question I wanted was why the double hash? And I forget what that... Double hashing doesn't prevent collision attacks since any collision is also a collision for blah blah. Yeah, so why the double hash? Maybe just to slow it down some more for each hash. We conclude the designer didn't want fast mining. Selected double hashing. Okay, to prevent length extension attacks, he selected double hashing. Okay. Yeah, length extension attacks are like a whole different issue where like you could give me a piece of data and I could arbitrarily extend like a preimage that you give me. Well, pretty much whenever you hash something, you always want to make sure that like if I'm asking to hash something, I want a certain size of data hashed. I'm sorry, I'm still trying to think of the best way to explain.
If you want 5 megabytes or what is it? Gigabytes? Megabytes? Kilobytes?
Right, exactly. If data hashed, then that's like what I want. Or going back to the lock combination. Let's say there's a certain lock that you're trying to find, a combination of a lock that you're trying to find. And I give you, I say, hey, you have to use these 3 numbers on this combination lock. And you're trying it out, but you know that there's a 4th number. I don't want you to use the 4th number, and I'm not expecting you to use the 4th number, but you can use the 4th number. And there is a way for you to use the 4th number to unlock the lock.
Without using the 3.
With using the 3.
With using the 3.
But using the 4 that I didn't want you to use.
Gotcha, right.
And that's what like a length extension attack kind of is. It's like
right. Not giving you all the information so that it takes longer to get the lock open.
Exactly. But if you're extending certain things arbitrarily without my desire or like without my intention, then you get these like length extension attacks. That's the quickest explanation I could make.
You're taking longer to do the work.
Right. Yeah. Sometimes I want you to take longer to do the work, or I want a certain precise hash. I don't want you having an extraneous data in it. But yeah, I see. This seems pretty repeatable. So I guess length extension attacks help fix this problem. Yeah. All right. Well, let me go back to here, compact blocks. Okay, yeah. So going back to compact blocks. You gave me a compact block. I look up the block index. If I didn't have the previous block, then and I'm not in initial block download, then I will maybe send get headers to you. So I'll maybe ask you for the headers of the previous block of the compact block that you sent me. And I hate these like maybe patterns of like, maybe. But yeah,
what does the code do if it says maybe? It's like,
there's like conditions on like whether it actually happens or not. Right. So here it says only allow a new get headers message to go out if we don't have a recent one already in flight. So it's like maybe it does it because it doesn't know like how fast you're sending these out. Mm-hmm. But if you sent one out like if you're sending them out too fast, then the next one will not send. So that's why it says maybe. This is a guaranteed to send to get headers. And this is just to prevent your node from generating too many different messages.
You don't want to get spammed, of course.
Right. You don't want to have your node give spam to people or other nodes to give spam to you because there's no form of throttling on.
Right.
Although there is protections against spam and the such, and maybe I'll spend the next last like 15 minutes going over that, going back to the original things that I said I was going to go over that I didn't really.
You're missing. We did.
Yeah. Maybe punish node for block. I wanted to go over this. What happens when like a pure lies or really just in general doesn't act in ways that we want it to. Maybe punish node for block is something that is kind of interesting. So let's look at that. Maybe punish node for block. Here, block checked. This is what I'm looking for. I think this is what I'm looking for. Process headers message. So sometimes when a peer gives me block headers, I check the block headers and find that they're invalid, occasionally. And when they are invalid, then I will typically try and punish you for the invalid block. And if we look into the invalid block punishment, there is a whole slew of different reasons or ways that I can punish you. So if you give me block headers and I said it was invalid, there's many things that constitute like in what ways it was invalid. And depending on certain ways that it was invalid, I will give you a misbehaving score. And I keep track of almost like a reputation score.
Score.
Yeah, exactly, like a social credit score amongst my nodes.
Right.
So if some are doing things I don't like, then I could, manage my connections to them or disconnect really.
So it's anyone below this number.
Yes, there is a threshold for disconnection.
Right.
So if you keep giving me invalid block headers in ways that were like very bad for it to be invalid, then I will keep adding to your misbehaving score, and eventually I will cut you off. Is how it works. I see a comment.
But you as an individual will cut them off, not the network.
Yeah, not the network.
Right.
Individual nodes cut individual nodes off, but.
So your node can be running with a number that's like super low, but like the network doesn't give a shit. So like,
Right, exactly. Yeah, you could say a node's like very bad. It's been bad to you, and it's like misbehaving. You mark that in your own personal data stores, but another node could keep it. It's like, hey, it's been great to me. It's never given me bad block. So yeah, these are like at the node level. Also, a few comments I see. Gimballock wanted to note that compact blocks were the result of all the research into speeding up block propagation. It knows all the transactions it already told you about previously, so just references what it already told you. So again, it's just another way to speed things up. In between the inventory message and between the block message, you have these compact blocks. He also said there was a high-speed relay network also that used every trick in the book, but all the tricks that could be rolled into the regular peer-to-peer network went into compact block design. Okay, so there was a huge movement, it seems, to try and get relay faster, and the compact block design was a result of that. Well, I think the relay is fast enough where it's gone pretty fast. But yeah, punishing blocks. You have these misbehaving scores, and yeah, you sometimes you will disconnect if a peer has been too bad. Maybe punish. Yeah, you can punish them for bad transactions. You can punish them for bad blocks. Here there was these other methods. Maybe discourage and disconnect. Let's look at that one. Maybe discourage and disconnect. So here, this is not it. This one. So now the misbehaving is, very important. You lock this mutex, should discourage. If the M should discourage, has permission. There's also banned nodes. There's also a way for you to set a node as banned. You'd never want to connect to it. That's what you see here. Is manual connection, not punishing manually connected peer. And if you there's again RPC commands that you could put towards your Bitcoin node, and if you manually connect to another node, it will never disconnect them for misbehaving. So if I connected to your node forcefully, if I put the command in and it wasn't naturally to the DNS seeds, if you misbehave, I will not drop you, or the node software won't drop you.
And I have to manually do it.
Huh? Yeah, I'd have to manually disconnect. If I manually added you, I have to manually disconnect you. So this is not punishing manually connected peer. See some comments. How do we punish all the ordinal attackers? The punishment for sending bad blocks is important to protect against chain splits. Okay. Or eclipse attacks. Yeah, if you're not connected to enough nodes or diverse nodes, I guess. Any bad blocks? Okay. Yeah, chain splits happen naturally, right? Even when you get errant blocks or when different miners are competing, when you get network segmentation and all this other stuff. But yeah, it's very good to keep track of nodes that give you bad blocks,
Mhm.
because some could just be made, maliciously. Yeah, so this is just punishment. Maybe discourage and disconnect. P node addresses local, does all these checks, and yeah, you have your ban manager, and you could discourage a node. So you have all these interesting things you could do to a node. Let's see, this other punishment mechanism I was referring to. Consider eviction. You could also evict nodes. There's a lot of like defensive programming in here to make sure that no one's trying to attack you over the relay. Not convict, evict. Was it evict node? No. Evict peer. Consider eviction. Consider eviction. It's right here. Yeah, so you can consider eviction. I wish they had like comments above every function. I think it would just make it easier to understand everything. But you get the state is outbound, or you can read the comments and see if we can understand the consider eviction through this. This is an outbound peer subject to disconnection if they don't announce a block with as much work as the current tip, within chain sync timeout plus headers response time seconds. If their chain has more work than ours, we should sync to it, unless it's invalid, in which case we should find that out and disconnect from them elsewhere. Okay. Well, let me see the context consider eviction is called. Consider eviction is called in just send, okay, yeah, this is send messages. Just consider eviction. I guess we always make this consider eviction call. I don't think it's in any weird condition. Yeah, all right, consider eviction. I guess we are always considering evicting this peer. Is outbound. It has to be outbound for this condition. Fsync started, which means that we're getting some blocks from them. Work header. Our best block known by this peer is behind our tip, and we're either noticing that for the first time, or this peer was able to catch up to some earlier point where we checked against our tip. Either way, set a new timeout based on the current tip. Okay, I guess this is just a way to keep all of our peers in check by seeing what blocks they have relative to ours, and how new they are, and what leeway we're willing to give them if they don't have new blocks, or they're stale blocks, or invalid blocks.
But that stays once it's implemented, they consider eviction.
Yeah, once they're evicted.
Or every time you connect to it, is it automatically?
Yeah, when you connect to it, you're constantly like processing the messages from it, and you're sending it any messages that you need to send it.
Every single time I get a message, I'm considering eviction.
Well, yeah, or every single time you're going through this loop of like reading your messages and sending someone else's, like sending your messages to the other peer. Yeah, you're considering eviction. So this is, I guess, maybe the best state. No evidence yet that our peer has synced to a chain with work equal to that of our tip. When we first detected it was behind. Send a single get headers message to give the peer a chance to update us. Okay, so I guess it's punishing bad blocks or in stale blocks and trying to disconnect to nodes that are giving too many stale blocks. Yeah. No, more for me to look at for sure. I just kind of like put them down because I was interested in them. Yeah, just a lot of code clearly in this file. This is all the network processing. 5,000 lines is not crazy. Give it enough time. Yeah, we'll give it enough time, right? Like, let's see another comment. I read that all the peer management strategies were borrowed from botnet login. Thank you, hackers, for all your hard work learning how to avoid being shut down. In a sense, you could think of Bitcoin as a botnet. Yeah, that is pretty interesting. I did not know that.
Botnet?
Yeah, peer management strategies were borrowed from botnet login.
Like a network of bots.
Yeah, I'm like wondering what the botnet login like is used for. Like if me and Mars had a bot, is that us sharing information about like what we logged in with? Or I guess if I'm a hacker and I have a whole bunch of instances, maybe, and I'm trying to synchronize my instances. Botnet logic. All right. let's look at bot. That's another rabbit hole for us to look at. Because yeah, botnet, logical collection of internet connected devices such as computers. Botnet logic.us. I don't think this is it, but but yeah, botnets are typically things people use for bad stuff, but this is putting it in a very positive light. But yeah, I think this is where I'll probably end for today. I know I was all over the place, but you know,
I couldn't tell.
it was a varied seminar with lots of different topics. Because again, it's very hard to choose one. Yeah, and I just thought it was better to go with the flow.
And it's all Bitcoin.
Yeah, it's all Bitcoin. And I went over the peer messages. It's just so much code, and I don't know how deep to get into all of the code. But you know, I think it's good that we're looking at the code at the very least and like getting
Right.
somewhat familiar with it.
Yeah, I feel like I could definitely. I got to probably take my own time out and go through it and like at least kind of know what I'm looking at as I'm reading it.
Yeah, recognize some things.
Recognize some things and just getting more familiar with it. Like that's all it's about. You know, so that's cool.
Yeah, I see Prav. Thanks for the code workshop. No problem. Thanks for still attending. Or yeah, thanks for being part of the live stream. All right, I guess I'll say bye to the live stream. See you guys. Thank you for coming. It's my first time trying this live stream, so hopefully it won't be the last. And yeah, catch you guys later. Bye.